Very much, Mark, and welcome everyone to this again, the 10th IJNA webinar. And today we have the pleasure of welcoming Dr. Rory Quinn, who will be speaking about mapping the future of underwater heritage, new insights from shipwreck science in the North and Baltic Seas. And this is based on an article that was published in issue 54.1, along with colleagues from National Museum of Denmark, Dr. David Gregory, and others. Also based at Ulster, which I'm sure Rory will present. And just to give some background on our speaker today, a brief introduction. He is a reader in marine geophysics at Ulster University, based at the School of Geography and Environmental Sciences. He received his Bachelor of Science in Geology from University College Cork, his Master's in Science and Geophysics from Durham, and his PhD in marine geophysics from the University of Southampton. And he has been based at Ulster since 1998 and has been involved in many different projects in marine geophysics, but also maritime archaeology. So without further ado, I'd like to welcome our speaker and welcome our guests tonight to this really exciting webinar.
Thank you very much, Athena, and thank you, Mark, for the introductions and for the invite to speak here today. So, as Mark and Athena said, I'm going to talk about the Endure project. And the reason I'm here is that David Gregory, who was originally supposed to be doing the talk, is caught up in a family matter. So Dave asked me to give you the talk. So, as Athena said, I'm a reader in marine geophysics here at Ulster University. Apologies from David, which I've given already. Why am I giving the talk? Well, Ulster University are partners in the Endure project with the National Museum in Denmark, and I'm the lead for Work Package 1, which is what the paper that was published in IJNA focuses on. Okay, so that's a bit in terms of the introduction. So first of all, a bit of project background to Endure. So it's funded by the European Union to the tune of 2.5 million euros, and it's a 5-year project, started in 2022 and is due to end in 2027. So the program it was funded under is the European Research Council, and David Gregory is the PI on the project, and Dave is based in the National Museum of Denmark, and others in the National Museum who are involved in the project include Andreas, Anna Maria, Arnes, Jan, Henning, and Christiana. And then at Ulster is myself and my colleague Chris. Chris is a marine ecologist. And then we've partners in the Sea War Museum in Thibron, Gert, Knud, and Christian. And then finally, we have the involvement of JD Contractors, and Rasmus and Mogans are the main people there. So there's a lot of people involved in the project, all under the leadership of Dave. And we all, I suppose, bring different sort of disciplines and different experiences to the project. And hopefully that'll become more obvious as we go through the talk. So here was this is a photograph taken actually at our first project meeting in Copenhagen. So that's David here. He's the PI in the project. And then here's a photograph, more recent photograph taken in Coleraine at Ulster in 2025, just a couple of months ago. So since the first photograph was taken, this is Jan Meiker. Jan did a lot of work on Work Package 1. So a lot of the work I'm going to present was done by Jan. Jan then left the project. He went to the commercial world, and since then we've had 2 new people join the project in the form of Craig here on the left and Andreas on the right. So that's just an introduction to or what the people look like. So what is the sort of main research question? What's the motivation behind the project, behind Endure? Well, we've all seen this statistic many times. UNESCO estimates there's about 3 million wrecks worldwide. So even if we look at the initial modeling domain we were looking at in the Endure project, within that domain there's about 54,000, just over 54,000 shipwrecks alone. And of course, UNESCO encourages in situ preservation of this resource. So how do we possibly preserve 3 million wrecks? Well, I think we'll all agree that it's kind of a difficult task to do that. So what Endure is trying to do is to pose the question and try and answer the question, well, how do we prioritize which of these wrecks might be most important to concentrate our efforts on in terms of in situ preservation? So I suppose that's the crux of the issue. So the overall aim then of Endure, Endure's ultimate aim is to propose a novel framework to cultural heritage management to examine the state of entropy of sites through methods and strategies for the sustainable preservation of underwater archaeology in the future. And I've underlined that term entropy here, and I'll talk to you a little bit about that concept in a minute. And we've got 4 work packages. The first work package is on remote sensing and spatial modeling. And that was the work package that I was leading. So that's what I'm reporting on mainly in this presentation. The second work package is titled In Situ Monitoring and Lab-Based Analysis. And the lead for that is Henning at the National Museum in Denmark. The third work package is Ecological Modeling, Fisheries Impacts and Socio-Cultural Values. And the lead for that is my colleague here at Ulster, Chris. And then finally, the fourth work package is Mitigation and Physical Protection. This is where we try and bring it all together. And the work package lead on that is David Gregory at the National Museum of Denmark. So in terms of progress, we've completed work package 1 at this stage. Work package 2, I would estimate, is probably halfway through. Work package 3 is about to begin hopefully in October, November time when we appoint a postdoc to it. And then work package 4 will then follow on once work packages 2 and 3 are almost complete. So I mentioned the concept of entropy a little while ago. Well, a simple way of looking at entropy is, I suppose, causing disorder from order, for want of a better word. So entropy is a measure of disorder. And this notion was first initially postulated by Boltzmann in the 1800s. So a simple way to think about this is if we've got a block of ice and we melt it, okay, we add energy to it. It goes from a very ordered state into a disordered state. So for example, if you melt the block of ice, you take a highly structured and orderly system of water molecules and convert it into a disorderly liquid in which molecules have no fixed positions. This is accompanied, of course, by a large increase in entropy during this process. So if you think of this as an analogy for a shipwreck, so when the ship is at the surface, it's nicely ordered. And oftentimes when it reaches the seabed, it's still nicely ordered. But slowly, but surely over time, it breaks down into a much more disordered state. And I suppose what we're trying to capture or understand better in Endure is this breaking down from this ordered state to the disordered state. And looking at the rates of that breakdown, how the magnitude of these sort of events that cause the disorder and also the rate of how quickly this breaks down. So we tend to treat shipwrecks as open environmental systems, and open environmental systems allow energy and material to flow across the system's boundaries. So if we're thinking of a shipwreck site, we might think of the energy here being hydrodynamic, so wave energy, tidal energy, that kind of thing. Material which might flow into a system would be something like sediment. And then we've got material energy coming out of the system, material in the form of sediment, but also bits and pieces of the wreck as it degrades and breaks off and then moves out of the system. And then the rate of that disintegration is dependent upon the physical, chemical, biological, and anthropogenic processes that act on that system. Okay, sorry. So just to reiterate there, the rate of the wreck disintegration is dependent upon physical, chemical, biological, and anthropogenic processes. And what we're trying to understand in Endure is the magnitude and the rates of these processes. So if we think of a shipwreck in terms of its system state, so it's generally in sort of semi-equilibrium with the surrounding environment. If something happens to that system in the form of a trigger, so that might be a natural event or it might be a cultural and anthropogenic forcing at the site, what happens is it tends to drive the system that little bit harder. Okay, and with a resilient wreck site, that wreck site, if it's resilient, will go back to its former state. Okay. However, if the system is driven and it isn't resilient, it will go into a new state. And if that new state is above a certain threshold, then the system has changed irrevocably. Okay, and we don't get the same system back. So something has changed in the system, and that can cause deterioration at a much faster rate. So these are the kind of things we're trying to understand in Endure. So our approach is the first phase, I suppose, of Endure was all about data collation and integration. And we used a lot of information from online and open source data portals. So we were interested in environmental processes and also human impacts. The second phase then, or the second stage of this, is all about remote sensing, in situ testing on actual sites underwater, and lab analysis from the samples we take from those sites, and also some computational modeling. Okay. And then finally, we are hoping to understand how best to preserve these sites in situ, as in the high priority ones, these low entropy sites, okay? These are the ones that we would prioritize for preservation in situ. And then these lower energy sites, low priority ones with high entropy states, these would go into effectively what we're terming here managed decay, for want of a much better word. Okay, so that's the essence again of the project. So in terms of work packages and how we're trying to address this equation, okay, work package 1 is all about understanding, I suppose, the physical and some of the anthropogenic impacts on these sites. Work package 2 really deals or concentrates on mainly sort of chemical and biological processes and the rates of decay at these sites. Work package 3 is dependent upon the biological and the anthropogenic influences. And then finally, work package 4 attempts to bring all of these together and to best understand what's happening at these sites. So it's a highly ambitious project, to say the least. Okay. So work package 1, I'll just talk to you a little bit now about work package 1. So I'll keep having to move this thing around. If I minimize it, might help. So work package 1 is titled Using Remotely Sensed and Legacy Data to Determine the Products of Decay. Okay, and I was the lead on this. Jan Meiker, David Gregory, Gert, Norman Anderson, Mogensdam, and Henning Mathieson were the other people involved directly in the package. Our tasks were, the first task was to investigate the state of wreck preservation based upon legacy multi-beam echo sounder data. And these data had been acquired by the Sea War Museum and JD Contractor over years. So we were very, very lucky to have this huge volume and this high density multi-beam echo sounder data set to work on. Our second objective then, or task, was to generate a GIS of the shipwrecks and to investigate their spatial distribution. The third one was to incorporate environmental and anthropogenic variables into the GIS and conduct some multi-criteria analysis to see what's correlating with between the archaeological material and the anthropogenic and environmental material. And then finally, we were tasked with identifying well and poorly preserved wreck sites for ground truthing and samples for decay studies. And we achieved all of that within work package 1. We finished it there probably about 12 months ago at this stage. So what techniques were we using? Well, we were using our main technique in terms of the remote sensing was using multi-beam echo sounder systems. So a multi-beam echo sounder system, the sort of primary product gives you is a depth layer, okay, very high resolution data in general. Okay, so it gives you the morphology or the shape of the seabed and also objects lying on the seabed. So this is a digital elevation model of a shipwreck in Belfast Lough in Ireland, and this has been surveyed using a multi-beam echo sounder. Myself and Chris, actually my colleague in Ulster, and a few other colleagues surveyed this site a few years ago. And just to give you an example of the sort of resolution we're talking about here, there's about 20 million data points in that image alone. And you're talking about a resolution, spatial resolution, probably about 5 to 10 centimeters on that side. So that's the kind of data that's achievable using modern multi-beam echo sounders. And then what we can do is use the multi-beam echo sounder data as the archaeological record effectively. And then we can compare the documentary sources and then try and understand about the coherency or the state of disintegration or otherwise of the shipwreck material by comparing one data set against the other. And then another derivative we can get from multi-beam echo sounders is something called backscattering. And we can use backscatter as a proxy for material properties of the seabed. Okay, so in that case, we can derive maps like these material properties of the seabed in terms of a geology map or a substrate map. So we can divide or partition the seabed up into different types of sediment, mud, muddy sand, sandy mud, sand, etc. Okay, and that has huge implications again for the site formation processes at these shipwreck sites. So just to give you an example from one data set, how we might use these. So these are multi-beam echo sounder bathymetry data. So what we're looking at here is dark blues are deep and then light blues are shallow. So we're looking at depth here in meters. And these are two shipwreck sites in Belfast Lough in Ireland. The one to the west here is SS Shirapo. She was wrecked in 1917. And the one to the right is Tiberia, and she was wrecked in 1918. So these are just the multi-beam echo sounder in terms of the bathymetric derivative. But from that, we can then derive things like local relief models. So what this is showing is the areas which are in blue are negative relief, and the areas which are in red are positive relief features relative to the overall trend in the data. So this allows us not only to image the shipwrecks, obviously, but all of these scour patterns, these depositional and erosional features around the shipwreck sites. And this can give us a lot of information again about site formation processes, about the hydrodynamics and the sediment dynamics acting on sites. We can also collect the backscatter data. So what you're looking at here is dark areas here are low backscatter, bright areas are high backscatter. So in general, low backscatter comes from soft or less rugged materials, and high backscatter data comes from hard and rugose or rough materials. Okay, so effectively what we're using here is the backscatter derivative to give us information about the geology and the archaeology of the seabed in terms of their material properties. Okay, and we can combine all of these data sets together to build up a much better understanding of what's happening at these sites and to characterize the sites. So the main output from our work package 1 was the IJNA article, which was published just last year in 2024. So what I'll do now is just give you a basic summary of that paper, I suppose. So the title of the paper is Using Open Data Portals, Remote Sensing and Computation Modeling to Investigate Historic Wreck Sites and Their Environments. 45 years on from Muckleroy. So we explored site formation processes at 549 wrecks in the North and Baltic Seas using multi-beam ecocenter data and environmental and anthropogenic variables. It's the largest just sole shipwreck focused multi-beam ecocenter data set that I'm aware of. Okay, as in 549 sites were surveyed specifically for the purposes of imaging shipwrecks alone. Okay, so this amazing work was done by JD Contractors and the Sea War Museum over about 10 years altogether. And phase 1 of the project, then we classified the structural integrity of each wreck using a modified Muckleroy approach. Phase 2, we used regression modeling to explore correlations between wreck class and environmental and anthropogenic variables. And then in phase 3, we used multi-criteria analysis to predict preservation potential across the full modeling domain. So this is our domain. So it goes from Scapa Flow in the west over into the Baltic in the east, okay, and takes in the North Sea. So for those unfamiliar with this area, we're talking about Jutland and Denmark here, okay, Norway and Sweden here, North Sea, Scapa Flow. So we had data from some of the wrecks in Scapa Flow, a lot of data from the North Sea, and quite a bit of data from the Baltic Sea. So each one of these red dots is effectively a shipwreck site that we had multi-beam ecocenter data from, 549 of them altogether. So in phase 1, just to remind you, we classified the structural integrity of each wreck using a modified Muckleroy approach, okay? And this is the workflow. I won't talk too much through that, but that's all highlighted in the methodology in the paper. So here I'm going to show you examples then of each one of these wreck classes, okay? So you'll notice here I have two labels. Preservation integrity is on the left-hand side, and that's increasing upwards. And then we've entropy on the right-hand side, and that's increasing downwards, okay? So the first class of wrecks were what we called coherent wrecks, okay? These were very much upstanding, very structurally intact wrecks, okay? They hadn't disintegrated a lot over time. So you can see the multi-beam expression of these here. So the colored one is a 2D expression, and the black and white one is a 3D expression of the wreck site, okay? Our second class that we classified then were incomplete wrecks. So these wrecks that were in good condition, but had started to degrade or break down. The third class were scattered and ordered. So there was still some order to these sites, okay? They looked like shipwreck sites, but they were disordered. And then finally, we had scattered disordered sites. So these were less intact, obviously, than class 3, etc. It was quite a subjective thing, as you can imagine. So this went through about, I think, about 6 iterations altogether, okay, of different people looking at them, classifying them, tweaking the system as we went along, okay. And what we found was in class 1, out of the total number, we had 76 sites. Class 2, the coherent incomplete, we had 126 sites. Scattered ordered, we had 157. Scattered disordered, 93. And then we had a fifth class, which either there was no wreck there or no visible wreck there, at least on the surface. or there was significant human impact in terms of there had been a lot of salvage done, and we were looking obviously at documentary records of all of these sites to look at salvage operations that had happened at a lot of these sites after World War I and World War II as well. Okay. So we couldn't include those in our analysis because we were kind of unsure of the history of them a lot of the time. So we concentrated our analysis on classes 1 to 4. So you can see here the spatial distribution of these sites throughout the study area. And it's very difficult to look at that map and discern any noticeable pattern or any discernible pattern. Okay. At first glance, it doesn't look very hopeful that there's any correlation there in terms, certainly in terms of the spatial domain. So to address that in phase 2, we use regression analysis modeling to explore the correlations between wreck class and the environmental and anthropogenic variables we were using to study. So what environmental variables did we use? We used depth, substrate, so sediment type effectively. We used current velocity, we used wave period, wave height, salinity, temperature, and dissolved oxygen. So we decided that these were the main 8 environmental variables that were driving site formation processes across the study area, and the ones that correlated with open data sources that we could get very, very good quality data for across that domain. Okay. So we used 2 main data sets for this. We used eMudNet, which is a European Union initiative, and it's an open data port that's fantastic. If you haven't played around with it, it's really worth using. And then the other one was a global database called bioRacle. So we got some of the environmental variables from that database as well. Okay. And Jan spent a lot of time processing these data and getting them all to speak to each other across the domain. And in terms of anthropogenic variables, the main one that seemed to be driving site formation process, or had the potential to be driving site formation process across the entire domain, was fishing activity. So you can see here some maps across the study area. Here on the top left, we've got bottom trawl interaction with the seabed. At the top right, we've got otter trawls, or sorry, beam trawls top left, otter trawls top right. Bottom signs on the bottom left, and the total fishing effort on the bottom right. Okay, so obviously the different gear types will have different impacts on the seabed, so we had to take that into account as well. So that was the main anthropogenic forcing that we included in the modeling. And then we did our correlation analysis. So what we were correlating here was the wreck classification against the environmental and anthropogenic variables, and seeing was there any explanatory power in those variables to sort of give rise to the fact that some of those wrecks were very coherent and others weren't effectively. And to put that simply, the output from that analysis was, the conclusions from that were that the depth, salinity, bottom fishing activity, and time, as in time on the bottom, were the significant factors in terms of wreck preservation. Okay, so depth, salinity, bottom fishing activity, and time. The rest of the variables didn't seem to offer any explanatory sort of power and any explanation in terms of what we were seeing in the data. Okay. So in phase 3 then, what we did was use these data and use a technique that's available in most GIS systems. We were using ArcGIS in this, but the same thing is available in QGIS. So it's called multi-criteria analysis or weighted overlay analysis. And we use that technique then to model the preservation potential across the entire domain from the results of phase 1 and phase 2. And this was our final model. So you can see here it's color coded. The greens show areas of high preservation potential. The reds show areas of lowest preservation potential. And then the oranges and yellows are sort of mid preservation potential. So you can see here we've got very good preservation potential up in the north of the North Sea, up into the Norwegian Trench. In the Baltic, unsurprisingly, we've got excellent preservation potential. And then in the North Sea, you've got variable preservation potential. In the southern North Sea, you can see these red areas, you've got very, very poor preservation potential. Along the east coast of, or the west coast of Jutland, you've got this very, very poor preservation potential. Up here off the north of Jutland, between the Jutland and the Norwegian Deep, you've got poor potential, etc. It gets better then as you go into the Baltic. So This was one of the big sort of wins for us, I suppose, in this work package, was to build this preservation model across the entire site. And from that, we were then able to identify where we had not only had zones of best preservation, but we also were able to identify it at a site-specific level, which sites were actually well preserved and which weren't well preserved. So from this analysis, we then highlighted sites for work package 2, where they're going to go in and monitor these sites and also to take samples from the sites. So and use that analysis in the use those samples in the lab analysis work package 2. So our main conclusions from this study were: the first one, weighted overlay modeling and regression analysis demonstrates that the structural integrity of wreck sites in the North and Baltic Seas is correlated with depth, salinity, bottom fishing intensity, and time. And Chris and colleagues then in work package 3 are going to look more into this bottom fishing intensity aspect. And then the second main conclusion was the study shows the potential of integrating high resolution remotely sensed data with environmental information from open data portals in predicting preservation potential of underwater cultural heritage sites across large geographic areas. So if there's any of you listening this evening that are interested in this type of analysis, EMONet has all of these data available for Europe, and BioOracle has many of these variables available on a worldwide sense. So another thing that we looked at in work package 2 then in a bit more detail was this potential influence of bottom trawling on the shipwreck sites. There was a beautiful publication came out last year, Threats to Our Ocean Heritage, Bottom Trawling. It was part of the Springer's Briefs in Archaeology and the Underwater Archaeology series, and the editor for this was Charlotta Jarvis. So we had a chapter in this. Lead author was Jan and myself, Gert and Dave all contributed to this publication. And we were looking at wreck sites as systems disrupted by trawling. Incidentally, Jan did his PhD here at Ulster with Chris McGonigal and myself. And this is a sort of bit of continuation of Jan's work that he started on his PhD and then continued into the Endure project. So the phase we were looking at here is when a shipwreck, so we're looking at here site dynamics on the vertical axis, time on the horizontal axis. And this is looking at the later stages of site formation process, when all of this really busy and high sort of energy stuff has happened in the initial phases. We're looking here at the later stages of site formation process, the impacts of fishing activity on these sites. So here's an example from the Irish Sea. This is one of the ones that Jan had used for his PhD actually. And this is a fishing vessel called St. Michan, which was wrecked in 1918 in the Irish Sea mudbelt. What you're looking at the center of this is the shipwreck here. So these are some multi-beam data. And what you're looking at here is a DM of difference. So the red areas are deposition of sediment. The blue areas are erosion of sediment here. And then what Jan has done is to use a multi-directional hillshade technique on these data as well to highlight subtleties in the data. And you can see these lines extending over these sites. Each one of these lines is effectively a trawl mark on the seabed. Okay, so you can see here on the larger inset image here, you can see a trawl mark has gone right across the site here, another trawl mark up here, another trawl mark across here, etc. So it looks here like we've got some direct or semi-direct evidence of trawling activity, certainly around the site, but possibly directly over the site as well in terms of this trawl mark here. We also then looked at other sites in the North Sea and in the Baltic. And from these two sites, the one on the left here is SS Edgar. We think it's SS Edgar wrecked in 1894, and the one on the right is unidentified sites. But again, on the SS Edgar site, you can see very convincing evidence for trawl marks in the multi-beam echo sounder data. And you've got a structural element measuring 4 meters by 1.5 by 0.3, which is dragged 32 meters along the bed. So this is this structural element here. And you can see it extends from the stern of the vessel and it's been dragged right over to here. Okay, so it's been dragged 32 meters from the site. So again, it looks like here we've got direct evidence of trawling on the shipwreck. Okay, and this unidentified site in the Danish North Sea, you can see here it's labeled with an intact boiler here. And then we've got a displaced boiler here. Okay, so this displaced boiler is definitely outside of the normal shipwreck shape here. So again, it's been displaced from the site itself. So I think these give fairly good evidence that we've got direct impacts of trawling on these sites. Now, this isn't very common, but it is in place. Okay, so we're going to investigate this further, and Chris and colleagues probably in work package 3 are going to investigate the process of these further. So the main conclusions from this bit of work were that bottom contact fishing has the potential to displace large and heavy structural elements such as steam boilers. Consequently, it can be inferred that trawling is also capable of moving unexploded ordnance and triggering the sudden release of pollutants to the ocean environment. This potential for pollution introduces another dimension to the importance of understanding and monitoring the impact of trawling on shipwreck sites. So that was basically what we did in work package 1 and the main results we've got from that. I'm now just going to go very, very quickly through work package 2, 3 and 4 just to tell you what they're going to do and how they're getting along at the moment. So this should take about 5-10 minutes. So work package 2 is all about the rates and the processes of natural decay. The first task is monitoring decay in underwater archaeological sites, and those sites have been chosen on the basis of the work that was conducted in work package 1. There will be laboratory mesocosm studies of decay in the form of a respirometer, and the respirometer was purchased and has been set up and has been calibrated and tested over the last 12 months. Arnis has done an amazing amount of work. He's got an amazing amount of patience, so he's been working on that over the last 12-18 months. The third element of that is to use finite element modeling to assess the form and function of the vessels. And then finally, the fourth task is to look at the molecular biological work on the organisms causing the decay at these sites. And just in terms of the people working on these, there's Arnis, Henning, Anna Maria, Anders, and Andreas, and David. So these are the people working on work package 2. So the new respirometer at the National Museum of Denmark has been set up and is working and is fully calibrated now. And they're using a respirometry to study the metabolic processes of the bacterial decay at these sites. A new DNA lab has also been set up at the National Museum of Denmark by Anna Maria, and she's using genetics to identify bacteria associated with the corrosion of metal wrecks and also anaerobic decay of waterlogged wood. And she presented some of those results at a recent meeting in Coleraine. Actually, they were absolutely fascinating to see the sort of resolution that she's looking at in terms of what the data is giving her. It's just quite phenomenal. So finite element modeling is going to be used to assess form and function of the vessel components. This hasn't been done yet. It hasn't been started yet as part of work package 2, but it will be up and running hopefully soon. So just to give you an idea of what that sort of means, there's a brilliant paper published here in Engineering Structures a couple of years ago by Afshar et al. And it was a full-scale finite element modeling and analysis of the 17th century warship Vasa, a methodological approach and preliminary results. So what you can do with finite element modeling effectively is build the structure of the vessel in a computer, and then you can give all of those structural elements properties based upon measurements that you would make in the real world. And then you can get the computer to basically model where the stresses on the structure, where the weaknesses in the structure, and then you can even try and sort of forecast, well, where is going to fail soonest in the future. So here's an example. Here's some examples from the paper. Here's the critical zones with the high stress values. So the sort of cold colors are the low stress values on the hull, right up to these very warm colors are the high stress values on the hull. So you can see where the high stress areas are. And then you can use this to start to model, well, what's going to happen in terms of what's happening at the moment and what might happen in the future. So there's a transverse cross-section showing vertical displacement, for example. And you can see these areas here are being displaced vertically. So again, the warmer colors, okay, are the areas which are being displaced vertically. The colder colors are kind of stable or sinking in these areas. So effectively what you can do, you can build a digital twin of the shipwreck, okay, and then you can give that digital twin the properties that you measure either underwater or in the lab or whatever, and you can get the digital twin to inherit those properties and then model what's going to happen to it in the future. So that's the FEM part of, that's the fourth task of the work package 2. Work package 3 then is the work package which is being conducted by Chris McGonigal, Craig Sims and Christian Tofgart. And this is ecosystem modeling and sociocultural values. And the tasks here are data compilation in terms of going to integrate the data that comes from work package 1 and work package 2. They're going to do ecosystem modeling as applied to underwater cultural heritage and also investigate the fishing impacts at the sites. And then finally, they're going to integrating socio-cultural values, and that's Christian at the Sea War Museum in Tiburon is going to be responsible for that. So Chris and a new postdoc will be working at UU on the first two tasks, and Christian on the third task. And then finally, work package 4, which is looking at the physical protection of underwater cultural heritage and curated decay. And the main people working on this will be Henning, Anna Maria, Andreas, and David, all at the National Museum in Denmark. And the tasks there are, one of the things they're going to look at is seagrass, okay, the use of seagrass to physically protect shipwreck sites. So they're going to grow, plant out, and then monitor how the seagrass is working on these sites. So seagrass, effectively, if you plant seagrass on a site, you're stabilizing the site, you're encouraging sediment to be deposited on the site, which will further seal the site and then prevent decay at the site. This is the high risk, high gain element of this work package, task 4.2, which is using sediment microbial fuel cells, or SMFCs, as an alternative to sacrificial anodes. And this is something Dave came up with and designed, and they're hoping to deploy this on at least one of the sites. So deploy this on specific ship elements, the frames and ribs of a site, etc., as opposed to surface deployment. So surface deployment would be mostly used for sacrificial anodes, but they're going to investigate how they could use SMFCs to basically deploy these on individual frames and ribs, which have been highlighted as weaknesses on these sites. And then task 4.4 is going to bring it all together, hopefully ranking these sites by entropy and selecting candidate sites for prioritization. So hopefully, when work packages 1 to 4 are totally finished, okay, we'll have a much better idea of what's going on in terms of this equation. We will have a better understanding of the magnitude and the rates of the physical, chemical, biological, and anthropogenic influences and forcing at these sites. And if any of you are interested in reading any more about it, we've got a fairly active website for the project called endureerc.com. So if you want to keep an eye on that over the time, we're posting sort of news articles and background information to the project, and any publications that we are publishing will obviously link to from that site. So it's maybe a nice way of keeping an eye on the project if you're interested and seeing how it develops over time. Okay, folks, thank you very much for listening, and hopefully we'll be able to answer some questions now as well if there are any.
Great. Thank you so much, Rory. That is really an incredible presentation, and there's so much going on with the Endure project that it's hard to kind of understand the amount of data that you're actually working with. It's including metal wrecks, a load of metal wrecks, and a load of also looking at the wooden shipwrecks. I'm going to go into the chat now. I think we do have some questions, perhaps. And we do have some Q's and A's here. And in the chat, we have posted, Mark has posted the link to the IJNA article, using open data portals, remote sensing, and computational modeling to investigate historic wreck sites and their environments, 45 years on from Keith Muckleroy. And let's see, we'd like to open the floor to any questions. There are no open questions or anything in the chat. Mark, do you see anything in the chat at this time?
No, unfortunately, no.
It's all clear. Well, I do have one question, and it's about as the work is mainly in the North Sea and the Baltic, is the methodology that you've introduced, Rory, for the project. Do you see that being transferable to other regions, like where you have other issues of salinity and temperature and just general chemistry of the sea, for example, in the Indian Ocean? Is a model that you can transfer in this way? Or your microphone is muted. There you are. Okay.
Yeah, sorry about that. Yes, absolutely. The idea would be that this methodology and framework would be globally applicable. So you would obviously need to set up models for each area, where there is a variation in salinity, temperature, etc., etc., and look at the correlation between those. But I think the key thing to come out of this is the overall understanding of the rates of these processes and the magnitudes and the influence that has on the structural integrity of the sites. But key, I think, is the methodology that's being worked out. It can then be applied anywhere once you've got access to that data. And I think that's the real strength of those data sets and the open data portals. So, for example, the eMudNet data portal covers the entirety of Europe, right into the Mediterranean, etc. It's not just the Baltic and the North Sea. That's the area we concentrated on in the first work package because that's where we had the multi-beam data for.
Yeah.
And then the other data portal is the BioOracle one, and that's just phenomenal. It covers the entire globe. So you can get all of those variables for the entire globe. So that methodology can be applied anywhere that you've got these data.
It's also, I think, very, very timely when there's been a lot of discussion about destruction through trawling. There's even issues with deep sea mining, and it's also been a huge subject about how to protect cultural heritage when we talk about the BBNJ agreement going through the biodiversity beyond national jurisdiction and how to address things like tangible cultural heritage, where these kind of decay rates are simply not known of certain shipwrecks. This is going to be really important to inform a lot of management protocols, for sure.
The fishing one is fascinating because the other side of that argument is if a fisher knows a wreck is there, they want to go near the wreck because there's lots of fish around it, okay?
Right.
That promotes biodiversity. However, they want to avoid it because they're fishing gear. So it's very expensive to lose your fishing gear, okay?
Yeah.
So there was a brilliant bit of work done a couple of years ago, as a paper published on that very fact, is that fishers are purposely avoiding, if they know the sites are there, they will have tried their best to avoid these sites, So it's a fascinating argument. So I think we need to build up more evidence about fishing practices and the actual impact of these. It's very easy to be scaremongering about these things. Oh, it's detrimental to this, but we need the data to back, we need the evidence to back it up, So there's I think there's a huge amount that can be done and investigated on that side of things, And I know Chris and his colleagues are going to look into that in Work Package 3 as well.
Okay, great. I think we do have a question here. We have several questions. Let's see here. We have, sorry, I have my glasses on here. So I'm absolutely fascinated by this enormous amount of work and your results. Brilliant. As a conservator and restorer, is there any space or PhD opportunities or funding for such professionals to integrate in this field of work, if you're within a conservation or restoration background?
Well, funny you should say that, but I know the National Museum in Denmark are going to be advertising a couple of positions over the next couple of years on that very part of it. So Jan Meiker, who did a lot of the work on Work Package 1, went to work in industry. So effectively, Jan had worked for, I think that post was there for 3 years, and Jan did 1 year work on it. So there's actually money that will be used for another postdoc and stuff at a later stage. And there's potential for a PhD coming out of it as well. So please keep an eye on the Endure website and also the sort of post that we will post about that. So there will definitely be opportunities. Yeah.
Okay, that's excellent to know for sure. We have a question here from Chris McGonigal. How do we deal with the fact that cultural heritage preservation potential is decoupled from the archaeological value of the sites?
I'll ask that question straight back to Chris. That's another area I think that there's a lot of, or an increasing amount of work being done on. So how do you decouple it? I don't know the answer to that, Chris. Hopefully you will be able to sort of elucidate some of those in the future. I know, Athena, from the work you're doing as well, there's an awful lot being done in that area in terms of the UNESCO work. Would you like to chat about that? Or?
Well, I can say that's a huge that's a topic for a whole nother webinar, isn't it? That'd be a nice roundtable actually to have a discussion about that in light of all the data sets that we now have, and this issue of how, especially when we're discussing, there's a lot of discussion. I mentioned the BBNJ, but also with NPAs and EIAs. that are coming into effect and requirements for those. This is a major question. How do you understand the potential of a cultural heritage, especially with the difference in differentiation sometimes between wooden shipwrecks and metal shipwrecks and submerged settlements and the environmental differences that different countries and regions are dealing with. That's a huge question. And then also not only that, but it's the value that you place on national and cultural values for a certain region of peoples or stakeholders or rights holders. So I think actually you're planting a seed, perhaps Chris and perhaps Rory and others, for a panel discussion that can really be enlightening.
Yeah,
So
it's fascinating. I kind of concentrate on shipwrecks. We're also looking at submerged archaeological sort of landscapes and sites and individual sites as well as part of Endure. But again, the scope of that in 45 minutes is difficult. So it is fascinating. Anna Maria presented some work in Coleraine there a couple of months ago where she'd been looking at some wooden posts.
Right.
And just, I mean, even a wooden post, one side of the post had been buried and the other side of the wooden post had been exposed. Okay. And the analysis she did showed two totally different site formation processes for both sides of them. And I think she thought it had only been moved relatively recently. Do you know what I mean? So again, a lot of these things depend on the scale and the resolution that you're looking at them as well. So these models that we presented here in work package 1 are very good for giving you overall patterns over large areas. Okay, but as soon as you start looking at something in higher and higher resolution and in detail, a lot of those patterns break down at the site specific level. Do you know what I mean? So, I mean, the amount of work to be done on this is just head wrecking in terms of how much, we do. And the big advantage I think we have now is the proliferation of these open source data sets. And at the moment, a lot of these are relatively coarse resolution, but all the time they're getting better and better and better. So the data is getting better. Our understanding, I think, is getting slightly better as well. So when these two things coincide, hopefully we'll be sort of able to address Chris's question in more detail, I suppose, as we go along. And yeah, as people become more aware of this, I think as well, and their attitude hopefully changes to using cultural resources in terms of their protection of areas, on a sort of wider scale, not just on the habitats or the biology of that area, but also, bringing it all together. So including underwater cultural heritage as a key element to this protection as well. Yeah. But they're all these things are linked, I mean, the shipwrecks are linked to the biology, which is linked to the geology, et cetera, And
it's like you're saying, exactly. It's going to come down to, for a lot of people on the regional and maybe national level, it comes down to scalability. That's going to be the major question of how can you take these large data sets and really pinpoint some specific to inform those management plans for sure. Yeah. So that's a very good question. I think that will lead to further discussion, and I appreciate that, Chris and Rory. We have another question here from Angeliki Zizi. So she thanks you for the talk, Rory, and she also is asking that are there nearly 600 wrecks, historical wrecks? If so, can the model be used for older shipwrecks, as she's calling archaeological? What was the correlation? That's one question. I think there's a few more parts here. Let's see. What was the correlation between entropy and time from wrecking? Are there physical and environmental variables weighted in the model? And if so, who decides the weight? Is there a parameter that proved to be the weakest or less predictable? So does the model have a weak point?
Okay, there's four things. I'll try and remember those.
Yeah, four things. So the 600 wrecks are historical, and can the model be used for older shipwrecks, archaeological shipwrecks?
So yeah, the 600 wrecks, they weren't all just modern wrecks. They were actually dated from, there were historic wrecks up to modern wrecks. By modern wrecks, I mean World War II wrecks, right?
Okay.
Where there were historic shipwrecks right up to. So A lot of them were metal wrecks, probably, yeah, there was probably three-quarters of them were metal wrecks, but about a quarter of them were wooden wrecks as well. Okay. So we're a range of wrecks, so it is applicable across the board in that sense. Um, Sorry, Athena, can you remind me the second part of the question?
What is, and the correlation between entropy and time from wrecking?
Yeah, so the correlation, very site specific again. Again, you can draw the patterns. Okay, in general, the older wrecks have undergone more entropy, for want of a better word,
Okay.
because they're there longer and they're exposed to the system. But it's very site specific because it depends on the shelter of the wreck, whether a high impact, short-lived event has had an influence on it. So entropy is very variable over as you look at it at a site-specific level, the entropy is highly variable, you know. So
Yeah.
you could have a wreck on the bed for 1,000 years, which has slowly degraded over time. Okay.
Mm.
Or you can have a wreck which has been down there for 100 years, but has been hit by one high impact event, and it can be very as degraded as the one that's been there for 1,000 years. So it is very site specific, I suppose, in that sense as well, which is really key to understanding the nitty gritty of these processes. We need to have more information about the sites. So the sites that are easiest to understand are those the ones that we have documentary evidence for and or that we've got some time series data for as well. And this is where Gert Norman Anderson has been phenomenal because he's been diving on a lot of these wrecks for 30, 40 years. So he's actually seen firsthand a lot of these sites, what's happened in them, and he can explain it. So you're sitting down with him, you're saying, oh, this, I'm looking at the multi-beam data, and he goes, oh, well, that used to be like this 30 years ago. Then there was a storm and this, so local knowledge on these sites is really, really important. I hope that addresses that part of the question.
It does. I hope it does, Dan Gillicky. She's got some more here. Are the physical and environmental variables weighted in the model? And if so, who decides the weight?
Yeah,
And
that weight was decided by, I should have explained that better, by the correlation analysis. So the preservation model inherited the weighting of the variables from the correlation analysis. So that's the beauty of that weighted overlay modeling or multi-criteria analysis modeling. You can get the data to inform your weighting of those variables. Okay. There's another really cool way of doing that. In the absence of that weighting and that correlation analysis, there's a technique called analytical hierarchical processing, a mathematical technique that you can use if you don't have all that information, and it's a way of kind of doing it a little bit more objectively than just a subjective approach to it. So that's called AHP, analytical hierarchical processing. We're using that actually at the moment to try and tease out other patterns at the moment. Yeah.
And that may already have informed the last question there. Is there a parameter that proved to be the weakest or less predictable? Do you
Yeah,
think the model has a weak point?
like a lot of these things, there's holes in the data. There's holes in our understanding of the data. A lot of the data in the open data portals, they've been combined by lots of people, huge amounts of effort. And say, for example, EBONet. EBONet basically brings in data sets from all the countries in Europe who are part of the EBONet project. So of course, when you come up to a boundary at sea between one jurisdiction and another jurisdiction, oftentimes there's quirky sort of artifacts in the data that don't always match. So it's difficult to eliminate those from your analysis at times as well. Do you know what I mean? So that's one weak point. Another weak point, Angelica, is the spatial resolution of the EBONet data that we were using and the bioOracle data is on an order of magnitude, well, a couple of orders of magnitude poorer than the spatial resolution of the multibeam data we were using, right? So we were trying to infer from very high resolution multibeam data patterns and classifications, but then we're combining with much lower order, much lower resolution data from the models. So you've got that weakness in the system as well. Do you know what I mean? So there's we could have a webinar about the weaknesses in this type of approach. There are weaknesses, but I think what we've done is the best we can do at the moment with the data. But as those open data portals get better and better in terms of the resolution of the data, then the technique will sort of be refined accordingly, I think.
Yeah, this is, I think that's the last question. And Gillicky says, thank you very much for answering those. And this is also, again, really time. Then we have maybe another question here.
There's a question in the chat, actually, Athena.
Okay, thank you so much. Let's see here. Okay. Evans here.
From Paul. Yeah.
Great, thank you. And will climate change have an impact on your modeling, especially salinity?
Yeah. The bioOracle modeling that I spoke about, that's the global open data portal, actually has future climate scenarios built into that. So that's our next step. We're hoping to include those future climate scenarios in another iteration of the modeling, and to see, Paul, to see exactly that, to see if what effect, say, changes in salinity, changes in temperature, etc., will have on the. So we did. I played about with that a little bit so far, but I'm not confident enough to give you any answers yet. But certainly it is possible, and bioOracle is beautiful in that sense because it's built, I think, 4 different climate scenarios into its outputs, so you can actually download projected outputs as well as current models from it. So yeah.
Be interesting when we hear these incidents of marine heat waves and things like that are really not very well studied in terms of cultural heritage, how that's going to impact. Again, like you said, very site specific.
We've had
data.
2 of those off the the west of Ireland over the last 4 years. So two marine heat waves, and like they're far in excess of what we would have experienced before. Like.
Yeah. Going through that 1.5 degree change. Yeah. Well, we don't want to end on a too morbid a note with climate change, but I think what this your presentation and the Endure project really reveal is that there's the rate and understanding of decay of shipwrecks has really been something that's hasn't been understood, and the data is out there, and the data is crunchable in a way to understand, and that's been really the gaping hole in understanding, not only from a scientific point of view but also from a management point of view. And that's going to be, I think, really, as you said, it's scalable and it's transferable. That's going to be something that's going to be really groundbreaking. So we look forward to seeing hopefully more publications in IJNA from the project, and really revisiting your data sets that a lot is open access. And again, I want to reiterate our thanks to Rory for taking the time and presenting this talk today. And also to remind everybody that the using open data portals, remote sensing, and computational modeling to investigate historic wreck sites in their environment, 45 years on from McElroy, the IJNA article published in issue 54.1 this year. It's open access. It remains open access. So please, if you are interested, go and visit our website and read the article. And with that, I think we don't have any more questions, but I think I will again thank Rory and thank our listeners for joining us this evening. This webinar will remain on the website. It'll be recorded, so you can revisit it at your leisure.
Thank you.
Thank you very much.
Thank you, Rory. Thank you, Athena, for today's webinar, and also pass on our best wishes to David. A big thank you to the Honor Frost Foundation for making this interesting educational experience possible. So on behalf of the NAS and our presenters, thank you for joining us, and of course for your questions. Enjoy the rest of your day or your evening, depending on where you are in the world. Goodbye.
Thank you, everyone.
Thank you. Bye-bye.